Imagine standing in a landscape that is just, well, completely covered in black volcanic rock,
Right.
and the ground beneath your feet is baking at 159 degrees Fahrenheit.
Which is almost hard to even wrap your head around.
It really is. I mean, it's a temperature hot enough to instantly cook an egg right there on a stone. The air is so thick with heat that it literally distorts the horizon into this watery mirage.
Yeah, a total optical illusion.
Exactly. And for decades, human explorers just called this place a dead zone. But then, darting across this scorching sand, completely comfortable in what should be, an uninhabitable oven, is a tiny lizard.
It's amazing. It completely defies our intuitive understanding of biology, You see an environment that basically represents the absolute extreme of solar radiation.
Yeah.
A place where geologists and meteorologists assume complex life just cannot sustain itself. And then boom, you find an entire ecosystem thriving right in the middle of it.
Which perfectly frames our mission for this deep dive.
Yeah.
Because you would think that finding the hottest place on Earth is just a simple binary task.
Right.
You think so, yeah. Just grab a thermometer.
Right. Like you just walk around the globe with a thermometer and wait for the mercury to peak. Almost like taking the planet's temperature to see if it has a fever.
That's a good way to put it. But the reality of how we measure extreme heat and how we actually define it, not to mention how biological organisms, including us, survive it, is incredibly complex.
Extremely.
The diagnostic landscape for planetary heat is just incredibly murky. I mean, we are dealing with moving targets here.
So true. And today, we're taking a massive stack of sources to try and find some clarity on this for you. We're pulling meteorological data from NASA's satellite records. We're opening up the historical archives from the World Meteorological Organization.
The WMO.
Okay, the WMO. And we're analyzing NOAA's comprehensive global climate reports, checking the Guinness World Records, and digging into some really highly surprising biological research from the journal Zootaxa.
It's a lot of ground to cover. But we are going to guide you through the fascinating and honestly often dangerous distinction between what the air feels like, what the ground feels like, and how scientists actually determine the true, quote-unquote, hottest spot on Earth.
Because looking at these sources, I mean, this isn't just an academic exercise in trivia.
Yeah, not at all.
We are talking about basic survival. And I want to start by looking at what extreme heat actually does to the human body. Because some of the numbers we're seeing recently in the data are just staggering.
They really are.
Let's look at a reading from August 2024. There's a weather station near Qeshm Darestan Airport, this is in southern Iran, and they recorded a heat index of 82.2 degrees Celsius.
Wow.
And for anyone listening who thinks in Fahrenheit, that is 180 degrees.
Which is just terrifying. That number pushes right up against and arguably way beyond the ceiling of human physiological endurance.
Yeah.
It is a terrifying threshold to cross.
But I want to be very precise here about what that number actually means.
Yeah.
Because the actual air temperature on that day was not 180 degrees.
Right, the ambient temperature.
Exactly. The standard thermometer reading for the ambient air was 38.9 degrees Celsius, so 102 degrees Fahrenheit.
Okay.
Now, obviously, 102 degrees is undeniably hot, but people live in 102-degree weather all the time, right?
Sure, yeah. Phoenix, Arizona hits that regularly.
Right. So the culprit that turned a standard hot day into a 180-degree lethal event was the relative humidity. It was sitting at an oppressive, suffocating 85%.
And to understand the physics of why that specific combination is so deadly, we really have to look closely at a measurement called the dew point.
Okay, let's get into that.
So during this extreme event in southern Iran, the dew point was recorded at 36.1 degrees Celsius, or about 97 degrees Fahrenheit.
A 97-degree dew point.
Yeah. And the dew point is basically the temperature to which air must be cooled to become completely saturated with water vapor.
I want to break down the mechanics of that for a second, because I think a lot of us hear, relative humidity and dew point on the morning news, and we just translate it to, oh, it's frizzy hair weather.
Right, exactly.
But it's actually about the carrying capacity of the atmosphere, isn't it? Like a sponge holding water.
That is a highly accurate way to visualize it, yeah. The atmosphere can only hold so much water vapor at a given temperature.
Okay.
So when the ambient air temperature and the dew point merge, when they essentially become the same number, the relative humidity reaches 100%. The sponge is completely full.
It can't take any more water.
It cannot absorb a single drop more. Now, apply the physics of that full sponge to the human body, because our primary evolutionary mechanism for surviving heat is sweating.
But the act of sweating itself doesn't cool you down, right? Like, I can be completely covered in sweat, but if it's just sitting on my skin, I'm still overheating.
Exactly.
The actual cooling only happens during the process of evaporation.
You're hitting on the exact mechanism there. The science behind it involves what we call the latent heat of vaporization.
Okay, latent heat of vaporization.
Right. When liquid sweat turns into a gas-water vapor, that phase change physically requires energy. The water literally pulls thermal energy or heat away from your skin to fuel that transformation into a gas.
Oh, wow.
And that energy transfer is what actually lowers your core body temperature.
So if we bring it back to that 97-degree dew point in Iran,
Right.
the atmosphere is already acting like a completely saturated sponge. The air literally cannot accept any more water vapor. So the sweat on your skin is just trapped in this liquid state.
It has nowhere to go. Evaporative cooling completely and utterly fails. You continue to sweat profusely because your brain is just sending these panic signals to your sweat glands, desperately trying to shed heat.
So you're just losing water.
Rapidly.
Yeah.
You lose vital fluids and electrolytes, but your core temperature continues to climb unabated. Your internal organs begin to face extreme thermal stress, and that drastically increases the risk of severe, rapid-onset heat stroke.
Which is terrifying.
It really is. Without medical intervention, this state can become fatal very, very quickly.
Let me try to put this into a visceral analogy for you.
Huh.
If you want to know what a 97-degree dew point actually feels like, imagine it's a really hot summer day and you are trying to cool down.
Okay.
But instead of sitting in front of a fan, you take a heavy blanket, you soak it in boiling water, and you wrap it tightly around your entire body.
That sounds absolutely awful.
Right. But that wet blanket effect is exactly what the heat index is trying to quantify. It's telling you that a standard thermometer reading of 102 degrees Fahrenheit is vastly underestimating the actual physical danger to your life because the air is just refusing to let your body breathe.
And when you look at the socioeconomic domino effect of those conditions, the implications are profound. I mean, when the heat index reaches 180 degrees, it isn't just a matter of discomfort anymore. Outdoor labor becomes physiologically impossible.
You literally cannot swing a hammer or harvest a crop.
Yeah.
The human heart and nervous system would just collapse.
Exactly. Industries like construction, infrastructure maintenance, agriculture, which, form the absolute backbone of many regional economies, they simply cease to function.
Yeah.
Societies are forced into this impossible corner. They either have to entirely restructure their civilization's working hours, perhaps shifting to completely nocturnal labor.
Which would bring massive disruptions, right, to
Yeah.
circadian rhythms, mental health, logistics.
Absolutely. Or they face a scenario where entire regions just become economically unviable and physically uninhabitable, forcing mass human migration.
To really underscore how specific this danger is to the moisture in the air, the sources give us a really great contrasting example of extreme heat.
Right, the Middle East.
Yeah, the Middle East is globally recognized for intense temperatures, but it's typically categorized by dry heat. For instance, there are these localized weather phenomena called sharavs.
Right, yeah. A sharav is a specific type of weather depression. It's typically a warm cyclone that occurs in the spring or early summer, and it basically pulls hot desert air into a region, causing a really sharp sudden spike in temperatures.
Right. And in July 2019, an incredibly unusual summer sharav hit Israel. In a location called Sedum, which is near the southern edge of the Dead Sea, the ambient temperature reached an astonishing 49.9 degrees Celsius.
Wow.
That translates to almost 122 degrees Fahrenheit. It was the highest temperature recorded in that country since 1942. But here's the critical physiological difference. The relative humidity during that specific sharav was sitting between 10 and 25%.
Which results in a completely different biological experience compared to southern Iran.
Totally.
At 122 degrees with only 10% humidity, the atmospheric sponge is basically bone dry. So when you sweat, the moisture evaporates off your skin almost instantaneously. The latent heat of vaporization is just working in overdrive.
You would dry out incredibly fast, though. You're losing water at an alarming rate.
Oh, you are. The risk of severe, rapid dehydration is immense. You had to constantly replenish your fluids. But, and this is the crucial distinction, your body's internal cooling engine is actually functioning.
Right.
The thermal energy is actively being stripped away from your skin. It is a profound thermal stress, but your body has a fighting chance to regulate its core temperature, unlike in the suffocating saturated air of a 97-degree dew point.
But this presents a massive challenge for meteorologists. I mean, if the actual danger to human life, the heat index, is so heavily dependent on these wildly shifting variables like humidity, dew point, and wind, how do scientists strip away all that noise to establish a fair, objective baseline?
It's very difficult.
Right. If we want to crown the absolute hottest place on Earth, we can't just rely on how the air feels to a sweaty human. We need strict rules.
And the scientific community does rely on a highly protected gold standard for this, overseen by the World Meteorological Organization.
WMO.
Exactly. You cannot simply stick a thermometer into a sand dune, take a quick picture, and claim a world record.
Let's examine those WMO rules, actually, because they dictate everything about our historical understanding of climate. The most important rule seems to be the height requirement.
Yes, the 1.5-meter rule.
Right. The thermometer must be placed exactly 1.5 meters above the ground, which is roughly 4 feet 11 inches. Why that specific height?
Well, it's designed to measure the ambient thermal energy of the air we actually inhabit and breathe. By placing the instrument 1.5 meters up, you are avoiding what physicists call the boundary layer effect.
The boundary layer, okay.
The ground absorbs solar radiation and heats the air immediately touching it through conduction. That bottom layer of air is wildly unstable and significantly hotter than the air just a few feet above it.
Makes sense.
So 1.5 meters gets the thermometer out of that chaotic boundary layer and into a more stable air mass.
And the thermometer also has to be entirely shielded from direct sunlight, right? The sources mention it's usually placed inside a specialized ventilated box called a Stephenson screen.
The Stephenson screen, yes. It's a brilliant piece of 19th century engineering that is remarkably still used today. It's a louvered enclosure, and it's usually painted white to maximize the reflection of solar radiation, what we call the albedo effect.
Ah, okay. The albedo effect.
Exactly. The louvers allow ambient air to flow freely across the thermometer inside, but they completely block direct sunlight and radiant heat from the ground. Because, if the sun hits the glass of the thermometer directly, you are no longer measuring the air temperature.
Right, you're just measuring how hot the sun can bake a piece of glass.
Precisely.
So using those incredibly strict standardized rules, 1.5 meters up, inside a white louvered box, where's the official hottest place on Earth?
This is where it gets really interesting.
Yeah, because this is where the historical data reveals a rivalry that lasted almost a century. For a very long time, the undisputed champion was a place called El Azidia in Libya.
Right. On September 13th, 1922, a weather station in El Azitia recorded a staggering temperature of 58.0 degrees Celsius.
Which is 136.4 degrees Fahrenheit.
Yes. And for 90 years, that number stood as the official, absolutely unassailable highest air temperature ever recorded on the planet.
90 years is an eternity in scientific record.
It really is.
That is generations of trivia books, encyclopedias, and Guinness World Records just constantly printing El Aziza as the absolute peak of planetary heat. But then the WMO decided to pull the thread on that data.
They did. In the early 21st century, climate researchers and weather historians began modernizing historical data sets. And they started looking at the surrounding synoptic weather patterns in North Africa on that specific date in 1922. And the 136.4-degree readings simply didn't align with the broader meteorological context.
It stood out too much.
Way too much. So a formal WMO investigation was launched. And in 2012, they published their findings and officially decertified the Libyan record.
They completely stripped them of a 90-year-old title. How does a mistake like that sit in the books for almost a century? I mean, the investigation found it wasn't even a mechanical failure, but human error, right?
Right. It was basically a cascading failure of standard operating procedure. Oh, wow.
The WMO concluded that an inexperienced weather observer was forced to use a complex, newly installed replacement thermometer. They hadn't been properly trained on how to interpret the specific index of this new instrument.
So they just read it wrong.
Essentially, yes. The investigation determined they likely read the wrong end of the indicator, which artificially inflated the recorded temperature by roughly 7 degrees Celsius.
One untrained observer reads the wrong end of a little metal stick in 1922, and it takes the global scientific community 90 years to correct the record. That is wild.
It really highlights the challenges of historical climatology.
Definitely. So when Libya was officially decertified in 2012, the Crown reverted back to the previous record holder, Furnace Creek Ranch in Death Valley, California.
Yes. And the Death Valley record dates back to July 10th, 1913. During an intense, prolonged heat wave, a weather observer recorded a temperature of 56.7 degrees Celsius, or 134 degrees Fahrenheit. The sources paint a terrifying picture of that specific week in Death Valley. I mean, from July 5th to July 14th, 1913, the high temperature reached at least 125 degrees Fahrenheit every single day.
Relentless heat.
The absolute peak of the heat wave was from July 9th to the 13th, where it hit at least 129 degrees each day, culminating in that 134-degree reading on the 10th. It just sounds like an absolute furnace.
It does.
But I have to push back on the WMO's logic here for a second. If climate historians were suspicious of a 1922 reading from Libya, wouldn't a 1913 reading from California be subject to the exact same skepticism?
You are echoing the exact concerns of modern meteorologists right now.
Okay, good.
The decertification of the Libya record effectively opened a Pandora's box of historical skepticism. Prominent weather historians, people like Christopher C. Burt and William Taylor Reid, have rigorously audited the 1913 Death Valley data, and their conclusions are highly critical.
What do they find?
They argue the 134-degree reading is essentially a meteorological myth. They suggest it is at least 4 to 5 degrees Fahrenheit higher than what the atmospheric conditions of the region could have physically supported on that specific day.
Interesting. Because I was reading through the various theories of how that 1913 measurement could have been corrupted, and there is a really brilliant piece of forensic meteorology put forward by Dr. Arnold Kort back in 1949.
Oh, yes, Dr. Kort's theory.
Yeah, he didn't think the observer simply misread the dial, like in Libya. He looked at the physical environment of Death Valley and theorized that a severe sandstorm might have corrupted the physical instrument itself.
Dr. Kort's theory is a masterclass in understanding extreme desert physics. He posited that during a localized high-velocity sandstorm, superheated surface materials, so hot sand, dust, and grit baking on the desert floor at well over 160 degrees, could be blasted by the wind directly into the Stevenson screen.
Even with the louvers pointing downward,
Yes.
a strong enough wind could carry particulate matter up and inside.
Precisely. And if the delicate glass thermometer is suddenly pelted by thousands of grains of sand carrying 160 degrees of radiant heat, it causes rapid thermal transfer to the glass through conduction. The thermometer experiences an artificial, localized spike. It is no longer measuring the ambient air mass. It is physically reacting to the impact of superheated rock.
Okay, this is where I really struggle with the WMO's stance.
I can guess why.
Yeah, if modern climate historians fundamentally agree the 1913 observer's data doesn't match the surrounding weather patterns, and we have these highly credible physical models showing how a sandstorm can artificially spike a thermometer, why does the WMO leave it on the books as the official world record? It feels like they are prioritizing administrative tradition over scientific accuracy.
I hear you. It really comes down to a philosophical difference in the burden of proof. The WMO operates on a highly conservative epistemological framework. To decertify a historical record, they require definitive, irrefutable proof of an error.
And they had that with Libya.
Exactly. In the Libya case, they could trace the specific installation of an unfamiliar instrument and physically map the exact visual error the observer made.
Right.
But for Death Valley in 1913, Dr. Kort's sandstorm is a highly plausible, maybe even probable theory. But it remains a theory. You cannot definitively prove a century later that a sandstorm hit that specific box at that exact hour.
Yeah, I guess that makes sense.
Therefore, the WMO maintains that until concrete, indisputable evidence of an error is presented, the historical logbook stands.
But if they were to finally bow to the pressure and decertify Death Valley 1913, the resulting landscape of world records is fascinating.
It really is.
They wouldn't have a single winner. We'd have a three-way tie spanning 3 different continents.
It showcases just how rare these upper limits of atmospheric heat truly are. Because if the 1913 record falls, the next highest reliably measured WMO-certified air temperature is 54.0 degrees Celsius, or 129.2 degrees Fahrenheit.
Okay.
And incredibly, human instruments have captured that exact temperature in 3 entirely different eras and locations.
Oh.
Yeah. At Furnace Creek in Death Valley in 2013, in Mitraba, Kuwait, in July 2016, and in Tirat Z, Israel, back in June 1942.
A 3-way tie for 129.2 degrees.
Yep.
The fact that the absolute pinnacle of planetary heat is locked in a century-old debate, or might actually be a 3-way tie across California, Kuwait, and Israel, really highlights the inherent flaw in relying solely on ground-based weather stations.
It's a very limited network.
And here's the glaring issue with the WMO's 1.5-meter rule. Nobody walks on the air.
Very true.
We walk on the ground. By elevating every single thermometer 4 feet 11 inches into a shaded box, we are purposefully ignoring the most violent thermal exchange happening on the planet, the point where the sun actually hits the Earth. So how do we measure the ground?
Well, we have to completely change our vantage point. We have to bypass the scattered network of ground thermometers entirely and look down from space.
And to understand why space is necessary, we have to look at the massive blind spots in our current system. According to WMO data, there are roughly 11,119 official weather stations operating globally right now.
Which sounds like a lot.
It sounds like a robust network, sure. But when you lay that over the total landmass of the Earth, it equates to about one weather station for every 56 million square miles.
It is a statistically microscopic sample size.
Yeah.
Furthermore, you have to consider placement bias. Where do humans build weather stations? We build them at airports, near agricultural hubs, at universities, and in urban centers.
Right, places where people actually live and need weather forecasts?
Exactly. The environments most likely to generate absolute peak temperatures, the hyper-arid, hostile, remote badlands and deep desert basins, they are largely unmonitored.
Because who is going out there to check the thermometer?
Exactly. It is financially and logistically prohibitive to install, calibrate, and protect delicate meteorological equipment in a constantly shifting sea of sand, hundreds of miles from civilization.
Makes total sense. So to fill those millions of square miles of blind spots, NASA utilizes a piece of technology called MODIS, the Moderate Resolution Imaging Spectroradiometer, which flies aboard the Aqua satellite.
MODIS fundamentally alters how we measure planetary heat. It is not interested in the ambient air temperature inside a Stephenson screen at all.
Okay.
It utilizes specialized sensors to measure thermal radiance emitting directly from the Earth's surface. In climatology, we refer to this metric as land surface temperature, or LST.
LST.
Right. Colloquially, it is known as the skin temperature of the Earth.
The skin temperature. And intuition tells us that the skin of the Earth gets astronomically hotter than the air.
Oh, without a doubt.
We've all experienced this. Think about walking barefoot across a black asphalt parking lot in the middle of July.
Right. Terrible idea.
The air around your head, that 1.5-meter mark, might feel like a breezy, manageable 90 degrees. But the moment your barefoot touches the asphalt, the skin of your soul faintly burns.
That analogy perfectly illustrates the physics of solar radiation absorption. The surface of the planet absorbs pure, unfiltered electromagnetic radiation from the sun. Without mitigating factors such as the cooling shade of a forest canopy, the lower atmospheric pressure of high altitudes, or the process of plant transpiration, where vegetation releases water vapor that cools the surrounding area, the ground temperature enters a state of thermal runaway.
Wow.
Ground measurements routinely exceed the overlying air temperatures by 30 to 50 degrees Celsius.
That is a staggering differential. A 50 degrees Celsius jump means the ground can be 90 degrees Fahrenheit hotter than the air you are breathing.
Easily.
So when NASA scientists calibrated the Aqua satellite to scan the globe for the absolute highest land surface temperature, the data crowd a completely undisputed king of heat. And it wasn't Death Valley, California. It wasn't El Azizi, Libya. It was a remote expanse in southeastern Iran called the Lut Desert, or Dashti Lut.
And the thermal radiance numbers pulled from the Lut Desert are difficult to even comprehend from a biological standpoint.
Yeah.
In 2005, the MODIS instrument recorded a land surface temperature in the Lut Desert of 70.7 degrees Celsius. That equates to 159.3 degrees Fahrenheit.
159.3 degrees. I mean, water boils at 212.
Mm-hmm.
You are well over the temperature required to slow cook meat.
You really are.
You could literally drop a raw egg onto the rocks of the Lut Desert and watch the proteins instantly denature and turn white.
And this wasn't just a statistical anomaly or a one-time glitch in the satellite data either.
Really?
No. Researchers at the University of Montana conducted a comprehensive 7-year study analyzing global land surface temperatures. In 5 out of those 7 years, the Lut Desert recorded the absolute highest surface temperature on the entire planet.
5 out of 7 years.
Yes. It is the most consistent, overwhelming thermal sink on Earth.
I know the Lut Desert took the crown 5 out of 7 years, but I'm curious what the satellite revealed about the runners-up. But where else on the planet even comes close to a 159-degree surface?
The MODIS data highlighted a few other extreme thermal zones. In 2003, for instance, Australia was gripped by a severe, prolonged drought. The lack of moisture stripped away the sparse vegetation in the Badlands of Queensland, exposing the raw earth directly to the sun. And the satellite recorded a surface temperature there of 69.3 degrees Celsius, or 157 degrees Fahrenheit.
Wow. 157 in Australia.
Yeah. Additionally, in 2008, the highest global surface temperature was found in China's Turpan Basin, specifically in a location aptly named Flaming Mountain, which hit 66.8 degrees Celsius or 152 degrees Fahrenheit.
So when we look at the Loot Desert, the Queensland Badlands, and the Turpan Basin, a pretty clear pattern emerges. What is the geological recipe required to cook the surface of the Earth to 150-plus degrees?
It requires a highly specific confluence of geomorphology, which is the physical shaping of the land and atmospheric physics.
Okay, so what's step one of the recipe?
First, you need extreme low elevation. Topography plays a massive role. Death Valley sits at 282 feet below sea level. The Turpan Basin plunges to 505 feet below sea level. As elevation drops, the weight of the atmosphere above it increases. This higher atmospheric pressure acts like a lid, basically compressing the air and trapping thermal energy inside the basin.
It's literally a geographical pressure cooker.
Exactly that. Second, you obviously need hyper-arid conditions, a total lack of moisture and vegetation.
Right.
But the final and perhaps most critical ingredient is the composition of the surface material itself. You need vast expanses of dry, rocky, dark-colored terrain.
Which goes back to the albedo effect you mentioned earlier with the White Stevenson screens. Light-colored environments, like massive white sand dunes or salt flats, reflect a significant portion of the sun's radiation back into the atmosphere.
Precisely.
But dark materials, like deep red sandstone or black volcanic basalt, they just absorb nearly all the available solar energy, directly converting light into heat.
The Lek Desert represents the perfect storm of these variables. It is a massive, low-elevation basin filled with incredibly dark, heat-absorbing rock. It basically functions as the world's largest, lowest, and darkest parking lot.
I am so fascinated by what it actually looks like to stand inside an environment that bakes at 159 degrees Fahrenheit. Because historically, places this hot are described as featureless voids, right?
Often, yeah.
The very name Lut in Persian loosely translates to bare land, devoid of water and life. It was considered such a hostile dead zone that even historical explorers like Marco Polo allegedly routed their caravans completely around it to avoid its deep interior.
They knew better.
Right. But when you dig into the geographical and biological sources we have, Dashti Lut sounds less like an empty void and more like a dramatically sculpted alien planet.
Oh, the geomorphology of the Loot Desert is spectacular, primarily because it is constantly being carved by relentless, violent winds. Between June and October, the region is subjected to strong north to south, southeast winds.
Okay.
These winds pick up abrasive particulate matter, basically turning the entire weather system into a continent-sized sandblaster.
Over thousands of years, that continuous sandblasting has sculpted three distinct, massive geological zones. I want to go through these because they're incredible. In the east, you have the Righi-Yellen. This is a sprawling sand sea containing active, shifting dunes that reach staggering heights of up to 475 meters.
Massive.
We're talking about mountains of sand taller than the Empire State Building.
It's incredible. And then in the western expanse, the wind has eroded the bedrock itself into massive corrugated ridges known as yardangs or kalous.
Yardangs.
Yeah. The scale of these formations is difficult to overstate. Some of these wind-carved bedrock ridges tower 155 meters high and stretch continuously in parallel lines for 40 kilometers across the desert floor.
Which is a 40-kilometer wall of carved rock.
Exactly. And then, nestled in the north, is the true oven, the Gandambarian Plateau. This area is covered entirely in black volcanic basalt lava.
Oh, the parking lot.
That's the dark asphalt we were talking about, the primary heat trap that absorbs all that solar radiation to push the surface temperature to nearly 160 degrees.
And the sources also mention these fascinating localized formations called nebkas, where there is even the slightest hint of subterranean moisture on the desert margins. Incredibly resilient desert shrubs somehow take root.
Right.
As the fierce winds blow sand across the basin, the shrubs act as a physical barrier. Sand accumulates on the lee side, the downwind side of the plant. Over time, this traps the sand into towering mounds up to 12 meters high, with the vegetation literally continuing to grow through the top just to survive.
So we have 400-meter sand mountains, 40-kilometer stretches of wind-carved bedrock, and a plateau of black volcanic glass boiling at 159 degrees.
It is so easy to see why humans wrote this off as a biological dead zone.
Absolutely.
But this brings us to the research published in the journal Zootaxa, which honestly completely shattered my understanding of what a habitable zone looks like. Researchers ventured into the Righi-Yellen megadunes and discovered that this extreme oven is actually a highly specialized ecosystem.
It forces us to entirely redefine the boundaries of biological endurance. The Zootaxa paper details the discovery of an entirely new endemic species of lizard thriving right in the middle of this heat sink.
Which is wild.
It is. It's a toad-headed agama named Phrenecephalus lutensis. And it is not a solitary anomaly either. The ecosystem supports various spiders and a specific insect known as the Lut cockroach.
How does an organism built of cells, water, and proteins not instantly perish? I mean, if you put a typical reptile or insect onto a 159-degree surface, its internal fluids would literally boil. Its cellular structure would disintegrate.
Biology conquers this extreme geology through a combination of brilliant behavioral strategies and highly specific morphological adaptations.
Okay, let's break those down.
The primary defense mechanism is chronological. Many of these creatures have simply shifted to become strictly nocturnal.
Makes sense, just avoid the sun entirely.
Right. They bypass the deadly surface temperatures by burrowing deep underground during the peak solar hours, only emerging to hunt and forage when the sun sets and the surface rapidly cools.
But the sources note that not all of them are strictly nocturnal, right? Some are active during the day. How do they navigate a landscape of boiling black rock?
They utilize the geomorphology we discussed earlier. They navigate via microclimates. Those towering 155-meter yardangs cast massive, long shadows across the basin.
Oh, I see.
And the wind tunneling through the corridors between the ridges creates localized airflow. An insect or lizard can dart from shadow to shadow, utilizing crevices in the bedrock where the ambient temperature is radically lower than the exposed basalt just a few feet away.
The physical bodily adaptations are what really fascinated me, though. The sources describe insects and reptiles evolving morphological traits specifically to counter the physics of thermal conduction. They develop incredibly long legs.
That is a brilliant evolutionary hack regarding the boundary layer we discussed earlier with the 1.5-meter thermometers.
Right.
The physical surface of the sand might be 159 degrees, but heat transfers relatively poorly through sill air. Just 1 or 2 inches above the baking sand, the air temperature drops precipitously.
So the long legs just keep them out of the worst of it.
Exactly. By evolving elongated legs, these creatures are essentially walking on stilts. They keep their vital organs and core body mass elevated in that slightly cooler boundary layer of air, preventing the direct, lethal conduction of heat into their bellies.
And for the creatures that need to burrow, they have adapted specialized techniques to dive beneath the lethal top layer of sand with incredible speed, reaching a depth of just a few inches where the sand provides profound thermal insulation, maintaining a remarkably stable and cooler temperature.
It's a perfect system for that specific environment.
It really is. Reading about the Phrenecephalus lutensis navigating these extremes really makes you step back and look at a bigger picture of life on Earth. If a complex vertebrate can evolve to thrive in a landscape defined by massive sandblasters and boiling volcanic rock, it feels like we vastly underestimate the tenacity of biology.
Life is relentlessly adaptable, but the critical variable in that equation is time. The fauna of the Lut Desert, the lizards and the insects, they've had thousands upon thousands of years of a stable, localized, extreme climate to incrementally evolve these highly specific, life-saving traits.
Right.
They adapted alongside the environment.
And that leads us to a deeply concerning realization about the rest of the planet, because the Lut lizard had millennia to get used to the heat. But right now, the global macroclimate is undergoing a rapid, unprecedented thermal shock. We and the ecosystems around us do not have thousands of years to evolve stilts or become nocturnal. We are watching the extremes become the baseline in real time.
If you look at the comprehensive data compiled in the NOAA Annual Global Climate Report, the velocity of the shift is undeniable. The report analyzes historical data sets stretching back 140 years. And in their 2019 report, they documented that 2019 was the second warmest year in the entire historical record.
But a single warm year could just be a statistical outlier, right? What makes the NOAA report so alarming is the clustering of the data. They highlight that, as of 2019, the 5 warmest years in recorded human history had all occurred since 2015.
Yes.
9 of the 10 warmest years have occurred since 2005. The baseline isn't just moving, it's accelerating.
The NOAA data strips away the localized anomalies and provides an impartial, stark view of the macroclimate. This overall rise in global average temperature doesn't simply mean winters are slightly milder.
Far from it.
It manifests as violent, prolonged, record-shattering weather events that push regional infrastructure and biology past their breaking points.
We saw exactly how that systemic warming translates into localized trauma in 2019. The report details how Europe experienced summer heat waves that completely rewrote their national record books. Meteo France, the National Meteorological Service, reported that southern France hit an unprecedented 46.0 degrees Celsius.
Which is 114.8 degrees Fahrenheit.
Prior to that event, they had never recorded a temperature over 45 degrees in their entire history. The Netherlands breached the 40 degrees Celsius mark for the first time ever. Germany, Belgium, the UK, multiple nations saw their all-time heat records smashed in a matter of days.
Simultaneously, the Southern Hemisphere was experiencing its own thermal crisis. The NOAA report details how Australia endured its warmest and driest year on historical record. That prolonged extreme heat and lack of moisture primed the landscape, directly fueling the catastrophic continent-wide wildfires that devastated their ecosystems.
As terrifying as 114 degrees in France or massive wildfires in Australia are, the sources indicate that focusing only on the air and land temperature means we are missing the vast majority of the crisis. We have to look at where all this excess thermal energy is actually being stored.
Yes, the continents only absorb a tiny fraction of the excess heat trapped in the Earth's climate system. Over 90% of that thermal energy is absorbed by the water. The oceans are the true thermal sink of our planet.
The ocean.
Right. And the NOAA report quantifies this using a metric called ocean heat content, or OHC. In 2019, the ocean heat content reached the highest level ever recorded, calculated at an astonishing 228 zetajoules above the historical average.
I want to pause on that unit of measurement because zetajoules sounds like a fictional power source from a sci-fi movie.
It does sound a bit out there.
A zetajoule is a 1 followed by 21 zeros.
Huge.
To put the sheer scale of 228 zetajoules into a human perspective,
Oh.
all of humanity, every factory, car, airplane, and power grid on Earth, consumes about half a zetajoule of energy in an entire year. So in excess of 228 zetajoules in the ocean is roughly equivalent to humanity running all of its industries and power plants at full capacity for over 400 years and dumping 100% of that energy directly into the sea.
That is a staggering amount of energy to inject into a system. And it is crucial to understand that thermal energy stored in the ocean is not dormant.
It's active.
Very. It acts as a massive high-octane battery for atmospheric chaos. The heat in the water constantly interacts with the atmosphere above it, driving evaporation and altering pressure systems. Thermal energy in the ocean translates directly into kinetic destruction on land.
The NOAA report gives a harrowing, tragic example of this kinetic destruction from that same year. The superheated waters of the Indian Ocean fueled a pair of unprecedented storms. Within a span of just a few weeks, two massive tropical cyclones, Idai and Kenneth, made landfall in Mozambique.
Right.
Cyclone Idai was one of the deadliest storms on record for the Southern Hemisphere, causing over 1,000 fatalities and billions of dollars in infrastructure damage. Then, mere weeks later, Cyclone Kenneth made landfall in northern Mozambique.
And the geographical data on Cyclone Kenneth is what is truly anomalous here. It struck an area of northern Mozambique where no major storm of that magnitude had ever been observed since the beginning of the satellite record.
Really? Never.
Never. It was the first time in recorded history that two major cyclones had hit that specific region in the exact same season. The excess zetajoules in the ocean essentially acted as an unlimited fuel supply, allowing those storms to intensify rapidly, sustain massive wind speeds, and hold unimaginable amounts of moisture to dump over the continent.
I think we can synthesize all of this, the global macroclimate and the localized extreme weather, by updating an analogy. We need to look at the Earth's climate system like a massive, closed pressure cooker sitting on a hot stove.
Okay, I like that.
We as humans living on land naturally obsess over the thermometer gauge sitting on the very top of the lid. The gauge represents the air temperature, the heat waves in France, the 1.5-meter thermometer in Death Valley. When the gauge spikes, we point at it and say, wow, it's getting really hot. But the actual danger, the engine driving the entire chaotic system, is the boiling water at the bottom of the pot. The oceans are the boiling water. They are absorbing 90% of the heat from the burner. And as that water boils with hundreds of zetajoules of excess energy, it generates violent pressure and chaotic steam, the unprecedented cyclones, the shifting global weather patterns that ultimately tear apart the delicate ecosystems living on the lid above.
That is a highly accurate synthesis of planetary thermodynamics. The rising air temperatures we experience, the heat index, the shattered WMO records, those are the symptoms. The staggering rise in ocean heat content is the underlying disease progression driving the extremes.
This has been an incredibly revealing journey through the sources. We started this deep dive talking about the murky, complex diagnostic landscape of planetary heat, and we have unpacked an enormous amount of data to find some clarity.
We really have. We have analyzed the system from multiple vantage points. We began by examining the ceiling of human physiological endurance, looking at that terrifying 85% humidity and 180-degree heat index in southern Iran. We explored the physics of the dew point and the latent heat of vaporization, understanding why sweat becomes utterly useless when the atmosphere acts as a saturated wet blanket.
We dug deep into the 90-year meteorological drama of the WMO's strict gold standard, unpacking why thermometers must be kept 1.5 meters off the ground inside a Stevenson screen. We traced the history of the 1922 El Azizia record being decertified and debated the controversial physics of Dr. Arnold Kort's theory that a superheated sandstorm may have artificially corrupted the 1913 Death Valley reading.
We then shifted our perspective entirely to space, utilizing the MODIS instrument on NASA's Aqua satellite to bypass the air entirely and measure the true skin of the Earth.
And found the Lute Desert.
Right. We discovered that the dark, low-elevation volcanic basalt of the Lute Desert operates as a massive solar radiation trap, baking the surface at nearly 160 degrees Fahrenheit.
We zoomed in on the biological miracles surviving inside that oven, marveling at how the Phrynocephalus lutensis lizard and the Lute cockroach utilize the fluid dynamics of wind shadows around massive yardangs and evolve long morphological stilts to stay in the cooler boundary layer of air just above the boiling sand.
Incredible adaptations.
Truly.
Yeah.
And finally, we pulled back to the macroclimate, using NOAA's data to realize that as our oceans absorb hundreds of zettajoules of excess heat, these hyper-extreme localized temperatures and unprecedented cyclones are rapidly becoming our global baseline.
It is a profoundly complex web of thermodynamics, meteorology, and evolutionary biology. And as we noted at the very beginning, trying to pin a single binary number on the absolute hottest place on Earth is an exercise in managing moving targets.
It truly is. But before we wrap up this deep dive, I want to leave you with one final mind-bending fact that we pulled from the Guinness World Records data. Because we have spent this entire time looking for the absolute hottest place on the physical ground or in the air just 1.5 meters above it. But technically speaking, the highest temperature ever reliably recorded on planet Earth does not occur in a deep desert basin. And it does not occur on a black asphalt parking lot. It occurs in the sky.
It is a phenomenal demonstration of extreme, instantaneous energy discharge.
According to the physical records, for a microscopic fraction of a second, the channel of air immediately surrounding a lightning strike is superheated to approximately 30,000 degrees Celsius.
Wow.
That translates to an almost incomprehensible 54,032 degrees Fahrenheit. It is roughly 5 times hotter than the visible surface of our sun.
5 times hotter.
Yeah. The sudden, violent, extreme heat is so intense that it physically splits the nitrogen and oxygen molecules in the air apart. When those fractured molecules rapidly cool and reconfigure, they form ozone, which is exactly why you smell that sharp, metallic, chlorine-like scent in the air immediately after a severe thunderstorm.
It represents the absolute pinnacle of terrestrial extremes. I mean, it's a temperature that defies our standard understanding of planetary physics, existing for just a millisecond before dissipating back into the storm.
So, bringing it all back to our initial attempt to diagnose the planet, maybe we will never be able to pinpoint the exact, continuous, undisputed hottest spot on Earth with perfect binary precision. The diagnosis will always be a little murky, caught somewhere between ambient air, volcanic skin, suffocating humidity, and century-old historical debates. But the next time you step outside in the middle of July and the heat radiating off the sidewalk makes you feel like the summer is absolutely unbearable, just take a deep breath, appreciate that your sweat is evaporating, and be grateful you aren't standing inside a thunderbolt.